Hi friends. So today I'm gonna do a presentation just to change things up, and it's just a little bit more about assembly. Uh, Wait, how do I operate the mouse over here? Okay, here it is. So just a refresher. These are your primary registers. So RAX, it's basically the return values for functions, and it's also the value used for some of the arithmetic operations. RBP is the base pointer, basically where you'll return to after a function. RDX is a, a it's a register used specifically for calling different functions. And then RSB is the pointer to the top of your memory stack. And those are some of the basic commands. So move something to somewhere else in memory, add to register or a register and a value in memory, subtract, multiply, and this new command is what we're going to do today, which is idiff. It is useful for basically it's used for integer division. So oftentimes, like in C or C++, you do the modulus operator, and this allows you to do that. So basically, you have a number stored in RAX, and you have a divisor, and then you perform integer division on those two numbers. And so the quotient will go to somewhere in memory, and the remainder will go to another place in memory. And the way you specify where it will go through are these commands. So for 8-bit, CBW means that the quotient will go to AL, your AL register, and your remainder will go to AH, and same with the other commands. So I think I have a sample program here written in C++, and then I basically just uh, turn it into binary. And so this is basically just finding the greatest common divisor of two numbers, and that's where the modulus operation comes in. So I'm gonna hop into IDA, which is a something that you can use to view assembly code.
Okay, I'll bring you up. Yeah, so just click new and just go and put it in assembly stuff. And we have this one. Yeah,
So this is what the assembly code looks like in IDA. And like normally, if you view assembly, it's in a text file, but IDA actually puts it into blocks, and then the jump commands are represented by these arrows, so it's easier to read. And it's also free, which
do you
is
want
what.
to zoom in so that way we can actually? I don't think we can like, see this.
Oh, I'm just gonna go to a specific function.
Or do you guys want to scoot up so that way you don't have we don't so that way you can actually see the smaller text? Because it's
So
kind of hard to see it from like back here.
yeah, so this is your. Oh, I see. Is there a way to zoom in here?
Just mouse scroll.
Mouse scroll.
Oh, I think you have to do like a control key.
Yeah.
Control and then yeah, that was
Yeah.
zoom in.
Oof. So yeah, this is where the modulus operation comes in, and then basically you move a variable into EAX, and CDQ. If you oh, oh, okay, back. So if you recall, CDQ means that EX gets sign extended to EDX, which means the quotient for the division will go into EAX, and the remainder will go to EDX. So we hop back to here. So you move a variable into EAX, you specify the sign extension, you do idiff, that variable, and basically what it does is it will take this value divided by that value, and EX will store the quotient, and EDX will store the remainder. And um, these are some things that we'll go into later. So this is how, if you want to write code in assembly, this is how you do a modulus. Everyone here, I think everyone knows what modulus and everything is, right? Okay, yeah. Uh, I don't know. I'm a freshman, so other freshmen doesn't really haven't gotten into there yet, that part yet. So this next bit is just a bit about memory. Um, and just a refresher, this is how memory works in assembly. So you have a stack, a heap down here. Heap goes upward, and the stack goes down. Data and text are stored at the bottom, and you have a stack pointer somewhere in there. It starts at the highest value, which is specified there. The hex value of 7 and a lot of Fs. And every time you allocate memory, the stack pointers move down. And every time, say you return from a function, the pointer moves back up, I think. Yeah.
What kind of system are you using that has 131 terabytes of memory in arithmetic?
I don't know. It's just, I don't know. It's just I don't think that's true. But I think that picture might be wrong in terms of the exact number, but the model of how the stack works should be should be good. Yeah. And then a bit about how you would allocate memory for local variables in your program. You would basically decrement the stack pointer. It says RBP, but it's actually RSP, the stack pointer. So suppose you want 32 bytes of memory, then you'll subtract 32 from 32 bits. Never mind. You subtract 32 from RSP, so you'll move the stack pointer down, and then the space that you moved by is where you can allocate memory inside and not have anything else that you call change that part of memory. So we have already seen it in IDA. Here, this part is where you move everything in. If you look at these commands, it's basically allocating 10. This is in hex, so 16 bits. 16 bits of bytes of memory, and it's moving values in register into that memory. So that's basically if you want to write assembly or read assembly, this is what a memory allocation looks like for local variables. Oh. So, here, I can probably just use mouse.
Yeah, you can.
And that thing again. So the next thing I want to go to is calling conventions, and it's basically specifying like how parameters will be passed to functions, and they pass parameters in this order. So the first parameter into a function will be RDI, then RSI, then RDX, RCX, R8 and R9. And if there are more, then I think they put, so these register will be pointers to memory, and the memory will store the actual parameters. So this is a simple program that I wrote to test out like how memory is passed into a function. And if I could open it up in IDA, it should be example 2. So yes, so this is the printf function. Wait, yeah, yeah. Oh. So this is your main function in assembly after you compile the code, and um, just like I said, you're calling printf, and the first variable to printf is a string that specifies the output format, right? So that string. It's stored in memory in another location, offset format. Anyways, it's just that string, and the second would be that first value. So the second is at ESI, so you move the second value 1 to ESI. Then the next is EDX, ECX, R8, and R9, just as we discussed in the slides. So this is how you push. You basically push parameters to functions. And so we'll be examining another example, which is the sieve. It's used to find prime numbers below a certain number. And so this program finds other prime numbers below 10 and print it out. So we'll take a look at how that looks in IDA. So in like how that code looks into assembly after it is compiled. And if any one of you have any questions, just please raise your hand and I'll. Where is main? So this is the start of the function, basically just allocating the local variables for the program. And the structure roughly looks like this. This is where your loop control will be, and then it'll pass to a fail state or a success state. The fail state would be if your condition right here. Oh, shoot. If this condition fails, then it passes to a fail state, and it'll exit out of the loop. And if you just look at the blocks, then this is the fail state, I think, which will pass onto another state to get out the loop. And then this is your main loop right here. And so if you examine this in IDA, this will be your main loop. And this will be where you print out a number to the stream. And this is where the loop will be terminated. So just an example of how you would follow different jump commands to basically examine your code in assembly. So, maybe you shouldn't. So the next step is writing an actual assembly program. And for your first one, this is just a hello world program. But I don't know if you've done this, but I want as an exercise for us to write something that reads in from the user input a number. So, and then output a number n, and then output the nth Fibonacci number. And since we already discussed how to pass parameters to functions and how to make local variables, I thought it would be helpful for us to write a recursive Fibonacci program. So if you recall, this is the recursive, the recurrence for Fibonacci. So the first two values are 1, and then the next are the sum of the two before it. Oh, And this is just a template I wrote in Mac um, that basically does hello world. If you want to start off, you only need the first 3 lines, the data section, and then write everything in your main and make another function for Fibonacci because we're doing recursive. So yeah, if any of any of you guys have any questions about how to start, you guys all have NASM, right? NASM? Oh, it's just something to compile assembly, I think. I think we got that the first day, but you could probably go online to find NASM and download it. Okay. Any other questions? Okay. But yeah, for reading and printing out, you should use scanf and print out. And yeah. You guys good?
Yeah.
Any concerns?
You might want to say that that doesn't actually work for.
Yeah, this actually doesn't work for Linux because it's
for
written
Mac, or for Windows or for Linux. So,
Windows or Linux because this is written on Mac.
So
Yeah.
if you are using if you're using Windows, I would actually use like the C functions, not the
Yeah.
syscalls,
Yeah.
because Windows actually doesn't expose the system calls. And if you don't know what I'm talking about, don't worry about it. So, do you have like some other assembly code for like just using the printf and that stuff?
Printf. Okay. Wait. Yeah.
Or like use those functions because I don't think this works on like
Yeah. Okay.
Mac.
Other than the solution, I guess you could look at the second example program where I actually use printf. And basically it's just you pass your wait, you guys can't see that. Okay. Is that clear enough? Yeah, you pass your format string into EDI, which is the first argument.
Pass an address, so
Yeah. Pass the address into the first argument, and then pass the other values into the other arguments.
do we want to do this one? Because this one is kind of more difficult.
Which one?
Like, does everyone know how to like define a memory segment for like a string? how do you define a string in assembly?
Right. It's like this, right? It's this part, right?
So
Yeah. Oh, okay. So this is like your data section. And
So,
yeah.
would you like to, can you explain like the label and what the label, the colon means and the DB, what does that mean?
Okay. So this is your label for the specific memory, and then DB I think is like the size of the memory,
Yeah.
and then you put a string in and a variable.
And so what do we do to pass, what do we pass into like the register in the previous example, in the using printf? So what will we actually pass?
We would actually pass, I think, the label in to the function. So the label goes into RDI, yeah, because RDI is your second parameter.
We have something called
All the sample projects.
Is that, so which one do you want?
This one.
Okay. Is that, that's thousands of them. See how, let me try to manually do this one.
Oh, okay.
Awesome. That's just, it's for different assembler. Product name.
That makes sense.
Feel free to like play around with code. Okay. Are all of you using SASM or the IDE? You're using it? I think the SASM actually has like examples of hello worlds that you can look at.
Yeah. And in case you want it, like you can search this up, but this is the order
Yeah.
for
Also, like
calls.
the order with the registers, we have to keep in mind that this order is for Linux and Mac,
Oh,
not
okay.
for Windows.
Okay.
I think it's different from Windows. Do we have anything else?
I think after this is just modify it like slightly to get like factorial, and then I think we should be done.
Okay. So actually, since we're talking about calling conventions, there's a website, you probably want to look it up, what's on your, you might want to look up what the call convention is, because it's different for different OSs. So here, I will actually pull up a browser, and then I think one of the best resources, if you just search up x86 call convention, is this one on Wikipedia. So I mean, if you search up x86 call convention on Google, it'll actually give you this Wikipedia page. So the idea is we have different call conventions. So the one that An was talking about is this systemd AMD64 one. So we can see that right here, this one. Can everyone see that? So we're looking at this line. Okay. Looking at this line. So we see that this is the order of registers when you pass in parameters. Right. So normally for something else, we actually have a different. So if we read this table, we see that for 32 bits, we have a few call conventions used by Microsoft or Windows, and most of them are actually used like this STD call, which is on the stack. But for 64-bit, we have something called Microsoft x64 call convention, and then these are the registers that they use. So we use RCX, RDX, R8, and R9, and those will be the order of registers. So that is kind of the difference. And if you can't remember those registers, you can always just search it up. Yeah.
Oh, sure.
Is there anything else you want to say?
It's just going over the solution, like, to the Fibble program.
Okay.
Yeah, if you guys fine with that. Okay. Ooh, you guys probably can delete this, but this is the entirety of the solution, for the Fibonacci program, and we'll break it down bits by bits and basically see how I did certain bits.
It's kind of small.
Yeah, I will. Like, you break it down and zoom it. So this is the first part. Data, basically, it's where I declared all the strings and all the variables I'll use if I ever store variables in data. In data. So that's the format for printf and scanf. You probably know like what those means.
So I noticed that I just asked you a question. So
Yeah.
I noticed how with X there's a DQ, and then for everything else there's a DB. What's the difference?
Okay. I think DB is like, okay. One is double, like quad word, and one is basically it's the size of memory. I'm pretty sure. And DQ should be bigger than the rest. Yeah.
So if you're just confused about that, the B in that stands for bytes. So think of bytes as like 1 byte.
Mhm.
Then you have the DQ. The Q actually stands for something called quad word, but basically it means it's something bigger, like a bigger integer.
Yeah. Okay. And that's where I declare all the functions. So all the labels, and this main Fibble is my Fibble function, and else it's not that important that you declare the last one. And then extern is similar to how you would include certain like libraries from in C++ or C. So that's the first part. Onto the main function. The first field is just maintaining the base pointer and the stack pointer. You push the base pointer onto the stack and then move the base pointer into the stack pointer. It's not too important. The next field, Leah, basically loads, I think it loads an address into from memory into a certain register, in this case RDI, and loads the address of X into RSI. And for some reason, you when you want to call scanf or printf, you have to make sure that EX is 0. So I did that right here, and so I call scanf, and the things it'll receive is first a string of the format, scanf format, right there. So this is the format of the string, and then an address where it will place the input in. So in this case, X will place the input from the user to the location which I labeled X in memory. And of course, EDI is the first parameter, and ESI is the second parameter. So next up, basically I just move the value that the user store into EDI, now it becomes the first parameter and call Fibonacci. And then I'll just walk you through the parts after. So after you call Fibonacci, right, it'll return a value. That value is stored in RAX by convention. And so I just load the printf format, which is found in memory in here. And I move the value x back to RSI because the way we print it out is Fibonacci and then n is equals to some value. So n is stored in x, so I move it into the second argument, and then I move the third value into the third parameter, and then you zero out REX, and then at that point you can call printf, and printf will take in this first parameter, the string, and then an integer to go into between the brackets, and then REX, which is the value returned from the Fibonacci function. And then afterwards, I just XOR REX to make sure that REX is 0. So oftentimes after C++ program, after the main function, you return 0, right? So 0 is the return value. It's at RAX. So I just make sure that it's 0. I leave the function and return. Leave, I think, pops off the stack pointer. Yeah, and then you would return. So this is the outline of the Fibonacci function. First few lines, again, is basically just managing the stack pointer. You can see the subtract stack pointer 24 right there, which is basically allocating 24 bytes in memory. Do you remember, like, we talked about that earlier? And then the compare, basically, it's comparing the, so it'll get in a number from EDI, the n Fibonacci, and it'll compare it to 1. So if it's less than or equal to 1, you just return 1, right? So the return value goes into REX, so move 1 into REX, and then you would leave, pop the base pointer off the stack, and then you would return. Otherwise, you'll have to do the recurrence formula, right? So I basically store n into a certain part of memory that I allocated earlier by doing the subtract 24, and then decrease it by 1, call fibble on n minus 1, obtain the answer. So now it's in REX, right? So I move the value of n that I store on there back to RDI, subtract 2 from that, so now n is n minus 2. And then, of course, I store REX into a part of memory, and then I call Fibonacci again. Now you would get the answer of Fibonacci n minus 2, and then you add it to REX, and then you leave the function. Oh, and before that, you should make sure that your RDI gets set back to n. Yeah. So that's pretty much it for what I have to say. Yeah. You guys have any?
Allocate 24 bytes.
Oh, honestly, it was just because I was too lazy to do the math. So I figured that 24 is like more than I needed. So that's why. But there's probably, you can probably do straight with less memory. Yeah. Yeah. It's, yeah. Okay. So yeah, that's your basic program in assembly. You guys should practice doing this. An easier version would be to program, what is it, factorial, because you only have to do one call recursive. So if you want to, I think this slide would be available, and you would just follow this like general format, and then try to make factorial on your own. That would be helpful because once you get a program running, you get an idea of how to do the next one. Yeah. Okay. Yeah. Yeah, that's about it for today. Were there any concerns, questions? No? Okay. Uh, wait, Henry, what do you guys usually do for like after the presentation?
I mean, we can have like do some practice if you want. So
Yeah. Wait, do you guys have this slide somewhere?
I
Or-
don't think so.
Oh, it's not posted yet?
Yeah.
Okay.
Oh, yeah, there wasn't like a notification like this week for me.
Huh?
There's no
Oh
notification.
yeah, I didn't send it out. Yeah.
Yeah.
Okay. I guess you guys, if you guys want to, you guys can get started with using this kind of general template to make the factorial program.